Imagine holding a soap bubble so delicate that merely looking at it causes it to pop. Now imagine that this microscopic bubble contains the blueprint for the next century of human technological evolution. This is the reality of the subatomic realm, where information does not exist as a simple 0 or 1, but as a fluid spectrum of possibilities. At the heart of this domain are qubits, the fundamental units of quantum computation that can exist in multiple states simultaneously through a property known as superposition. They can also share a ghostly, instantaneous link across vast distances, a phenomenon called quantum entanglement, where the state of one particle dictates the state of another regardless of the space between them. Yet, capturing and holding on to these profound states is an agonizingly difficult endeavor. How do we build a vault for something that destroys itself the very moment it interacts with the outside world? Explaining the rapid loss of this information requires understanding a phenomenon known as decoherence. Decoherence is the process by which a subatomic system loses its delicate state and collapses into classical, mundane reality. A stray photon, a microscopic fluctuation in temperature, or the faint magnetic hum of a nearby wire is enough to shatter the superposition. The information simply bleeds away into the surrounding environment, lost forever. This fleeting nature is the unseen bottleneck preventing the true potential of advanced computation and communication. Storing this fragile data requires an entirely new discipline of science, pushing the boundaries of what is physically possible to isolate these particles from the chaotic noise of the universe. To fight the relentless march of environmental interference, engineers must construct environments of profound isolation. One leading method involves trapping individual atoms within complex webs of electromagnetic fields, suspending them in a perfect vacuum. To prevent the atom's own thermal energy from destroying the stored data, scientists plunge these traps to temperatures approaching near absolute zero. At a fraction of a degree above minus 273.15 Celsius, atomic motion grinds to a near halt. In this frozen silence, the delicate states can survive just a little longer. Yet, maintaining such extreme conditions requires massive, energy-intensive refrigerators, making the widespread deployment of these systems a monumental hurdle for engineers to overcome. While some researchers build massive cryogenic freezers, others look to the inherent structure of precious stones. A remarkable alternative to ultra-cold vacuums is found in diamond quantum defects. By carefully engineering ultra-pure synthetic diamonds and intentionally removing a single carbon atom to replace it with a nitrogen atom, scientists create a tiny, naturally isolated pocket within the crystal lattice. This defect acts as a cage, shielding the fragile qubit from surrounding environmental noise while allowing it to be manipulated by precise pulses of laser light. The brilliant promise of these crystalline vaults is their ability to operate at room temperature, potentially freeing this technology from the constraints of massive infrastructure. The implications of successfully storing this information extend far beyond laboratory curiosities. Mastering quantum memory is the foundational step toward realizing a global, interconnected, subatomic internet. Unlike our current digital networks, which transmit easily intercepted pulses of light or electricity, a next-generation network would use entangled particles to send data. Because observing these systems inherently alters them, any attempt to eavesdrop on this network would immediately corrupt the transmission, instantly alerting the users. This promises an era of truly unhackable communication, fundamentally reshaping global security, financial systems, and the privacy of human data. But transmitting such delicate signals across continents without them degrading into useless static requires overcoming a massive physical barrier. The fragility of these entangled links over long distances presents a formidable challenge. Fiber optic cables, the backbone of modern telecommunications, naturally absorb photons over time. In a classical network, amplifiers simply copy and boost the fading signal. However, the laws of physics strictly forbid the exact copying of an unknown subatomic state. To solve this, engineers are developing quantum
X-ray stations do not copy the signal. Instead, they catch the fading entangled photons, store them briefly in a memory vault, and then perform an intricate operation to chain the connection to the next segment of the network. Without robust, long-lasting storage at each relay point, the signal simply perishes in the dark glass.
Even with perfect repeaters and diamond vaults, the chaotic nature of the universe guarantees that anomalies will eventually creep in. Protecting the data over extended periods requires the implementation of quantum error correction. In classical computing, correcting mistakes is simple. Make 3 copies of the data, and if one flips by mistake, the majority rules. But because these states cannot be copied, and merely checking them destroys their superposition, scientists had to invent an entirely new mathematical paradigm. They spread the information of a single logical qubit across dozens or even thousands of physical qubits. By carefully measuring only the relationships between the adjacent particles rather than the data itself, algorithms can deduce and fix anomalies without ever collapsing the core information. The successful orchestration of memory vaults, repeaters, and error correction will finally unlock the era of fault-tolerant computation. These machines will not just be faster, they will solve complex chemical and physical problems that are fundamentally impossible for classical supercomputers. By accurately simulating the intricate dances of molecules, researchers could design highly targeted pharmaceuticals tailored to individual genetic profiles, effectively ending certain diseases. They could engineer revolutionary new materials for efficient energy transmission, or discover catalysts that pull carbon directly from the atmosphere. The ability to hold and manipulate this fragile data is the key to unlocking a new industrial revolution. Yet, the sheer power of this impending revolution casts a long, ethical shadow over global society. The same computational supremacy that promises miraculous medical breakthroughs also threatens the cryptographic foundations of our modern world. A fully realized, fault-tolerant machine could effortlessly shatter the encryption protocols that currently protect international banking, government secrets, and personal privacy. The race to build stable storage is therefore not just a scientific pursuit, but a high-stakes geopolitical battle. The first nation or entity to master this technology will possess an unprecedented advantage, forcing humanity to urgently transition to highly resistant cryptography before the ultimate code-breaking machine comes online. Beyond the geopolitics and the engineering marvels, this endeavor forces us to reconsider the very nature of information itself. For all of human history, a memory was a physical mark, ink on a page, a magnetic charge on a hard drive, a synaptic connection in a biological brain. But this new form of memory is profoundly different. It is an attempt to bottle the probabilistic nature of the universe itself. We are learning to capture a fleeting whisper of reality before it decides what it wants to be. The act of storing this information is an act of holding time and probability in a state of suspended animation. The progress in this delicate art of suspension is accelerating rapidly. Not long ago, holding a state stable for a few microseconds was considered a monumental triumph. Today, researchers are pushing coherence times from microseconds to seconds, and in some highly specialized setups, even minutes. Through relentless refinement of materials, better shielding against cosmic rays, and increasingly sophisticated algorithms, the vaults are becoming stronger. The entangled particles still echo their strange connection with greater resilience than ever before. Every fraction of a second gained is a hard-won victory against the fundamental entropy of the cosmos. As we look toward the horizon, the mastery of these fragile states suggests a profound shift in humanity's trajectory. We are moving from a species that merely observes the universe to one that actively engineers its underlying fabric. The technologies born from this engineering battle will likely become the invisible infrastructure of the next century, operating silently in the background while enabling feats of computation and communication that seem like magic today. We are building the nervous system of a future civilization, one that processes reality in a fundamentally different way than we do now. The battle to store this delicate information is far from over. It remains a continuous war of attrition against the natural tendency of the universe toward chaos. As we build colder traps, purer diamonds, and more complex mathematical shields, we edge closer to an era where the subatomic realm is fully domesticated. But as we finally lock away the fundamental secrets of the cosmos in these microscopic vaults, we are left to wonder what unimaginable realities we will unlock when we finally hold the keys.